Okay, so it's 17th of October, 2017, and we are talking about the most fundamental bits of the atom here. This is a primitive view. This would be basically Rutherford Bohr that we're looking at here in terms of what model of the atom. We got protons and neutrons in the nucleus. We got electrons somewhere on the outside. We're not going to clarify that a whole lot. In the next chapter, you're going to learn more about where those electrons are than you ever thought you wanted to know, as a matter of fact, than you ever did want to know, because we're going to give them very specific addresses. But for now, it's enough to just say they're outside the nucleus. Okay, here are some bits. In that nucleus, you have protons, which have a positive charge, pro-positive, and a mass. I want you to grasp how tiny that is. 1.673 times 10 to the negative 27th grams. We don't have a prefix for that. The smallest prefix that I'm aware of is exa, which is times 10 to the negative 18th. So even if we use exa, we're below that. This is infinitesimally small. We have neutrons, which have a mass of 1.675 times 10 to the negative 27th grams. Also, really stinking little. Now here's what's interesting. If you have two positively charged particles, what would you expect them to do? Two like charges. What do we expect those to do? Repel. Like charges repel. I hope it doesn't do that on the actual video. In a nucleus of an atom, we've got all these positive charges packed in together. Why doesn't the nucleus just explode? There are four fundamental forces in the universe, and one of them are what are called nuclear forces. And so this is one of those very strange things where it seems like the rules are a little bit different depending on the scale we're talking about. Inside the nucleus of an atom, those positively charged protons are actually attracted to one another, and there are strong and weak nuclear forces, but we don't need to know that. They are attracted to one another by nuclear forces, which sounds crazy, and I am not enough of a physicist to explain more than that, but suffice to say, all the matter around you is, as far as we know, going to continue to be held together by those nuclear forces, so I'm not worried about stuff just randomly disintegrating, which is a good thing. That lends a degree of certainty to my day. When we talk about measuring atoms, we measure them in picometers. We typically measure things like bacteria and human cells in micrometers, so atoms, of course, which make up those things, are much, much tinier. And the radius of the nucleus is about 1,000th of a picometer, roughly. And again, there's no handy prefix unit for that, so we just say, yeah, it's 10 to the negative third picometers. Okay. Now, atomic mass. You probably did some of this somewhere in physical science. You may or may not remember it. Atomic mass, the shortcut we use is the atomic mass is equal to the number of protons plus the number of neutrons. We measure it because particle physicists and chemists are incredibly creative. We measure atomic mass in atomic mass units. Very hard to remember, I know. Protons and neutrons are not equal in mass. This is the great lie you've been told. So if we go back and look here, those are not equal. They're really stinking close, but they're not equal. But we just assign that mass. We assign them each a mass of 1 AMU. Okay? So for every one proton, we add 1 AMU to the mass. For every one neutron, we add 1 AMU to the mass. So basically an AMU is, what, 1.67, either 3 or 7 times 10 to the negative 27th grams. You don't need to know that conversion factor, I assure you, but you do need to know that AMUs are how we measure atomic mass, and that one proton has a mass of 1 AMU and one neutron has a mass of 1 AMU. All right, so what I gave you is the Van Brainer periodic table. I use a couple different versions of this throughout the year. You'll notice a few things about the Van Brainer periodic table. You'll notice that the Van Brainer doesn't list the name of the elements. It just gives the atomic symbol. I think it would be really stupid to tell you that you have to memorize the atomic symbols. I think that's dumb. You can look those up. You can use a periodic table once you leave my class that has all the names written in. I'm not going to ask you to memorize them. However, by probably December or January, I'm going to assume that if I put on a test or a quiz, C, you know that's carbon. I'm going to assume by December or January that if I put on a test, lithium, you're going to know what that is. And you know what? Here's the magical part. You will. So I'll start off using, lithium apostrophe or, parentheses, Li. And you will learn them by using them. That's how you memorize information, is by using it. And I'll give you plenty of practice at using it so that you will know pretty much, you're going to know the most common ones. Whoops. So you're pretty much going to know all of these, and probably a good portion of the metals out in the middle. Now, how do you find the number of protons on the periodic table? Talk it over at your table. Don't yell it out. Did you all get your periodic tables? Talk it over at your table. How do you find the number of protons on that table? How do you find the number of protons? I'm spying on you. So keep discussing amongst yourselves. I'm sorry, Colin. You can move to a table with actual humans to talk to, because I feel like you have to talk to yourself. Is there a specific number on that periodic table that shows you the atomic number, that shows, oh, no, there we go. Oops. That shows you the number of protons? Why, yes, it is, Moser, and you just let the cat out of the bag. It's the atomic number. So the atomic number is the small whole number over the symbol on this table. In some periodic tables, it's given in different locations. The Van Brainer always gives atomic number above the atomic symbol. And that atomic number is the number of protons. And you'll notice on this, we go 1, 2, forget about that second hydrogen, 3, 4. It just keeps increasing. The periodic table is arranged in order of increasing number of protons. So it's arranged in order of increasing atomic number. Okay, that part's pretty easy. Okay, so tell me how many protons any atom of aluminum has. Discuss it at your table. So aluminum is Al. How many protons? Yeah, aluminum has an atomic number of 13, therefore it has 13 protons. And sometimes we abbreviate that by just writing, I write 13 protons, I write a little plus sign. Okay, that's fairly easy. Now we're going to talk about isotopes. So an isotope is an atom of an element that has the same number of protons, because they have to have the same number of protons. If you change the number of protons, you change the element. If it doesn't have 13 protons, it's not aluminum. If it has 12 protons, it is not aluminum. If it has 14 protons, it's not aluminum. If I have any Monty Python fans in here, I'm thinking and the number of the counting shall be 3. Not 4, not 5, 2 is right out. Isotopes of an element have different numbers of neutrons, and therefore they have a different atomic mass. Because we said the mass number is equal to the number of protons plus the number of neutrons, finding out the number of neutrons is simple algebra. We take the mass of the isotope and subtract the atomic number. Because the atomic number is equal to what, Matt Tabacco? Atomic number is equal to number of protons. Right. So if we take the mass and subtract the number of protons, we get the number of neutrons. Now, isotopes are named for their mass. This is like who's buried in Grant's tomb, folks. Who is buried in Grant's tomb? Oh, please get this right. Grant. It's Grant's tomb. Grant's buried there. So, carbon-14 has a mass of, all together now, 14! Cobalt-60 has a mass of 6. 60! Now we should be putting units on that, so it would be 60 AMUs because we measure atomic mass in, oh my god, these are all Grant's-Tomb questions, atomic mass units. This seems really straightforward, right? Good. I'm going to shrink this. And I will guarantee you that at some point I will ask a question like, what is the mass of sodium-23? What's the mass of sodium-23? 23 AMUs! And somebody's going to get it wrong. And I'm going to be sitting at home on the couch grading, and I will growl, and my husband will go, what? I'll say, it's an isotope question again. So don't be the one who makes me growl. Don't do it. You won't, I know. So how many neutrons does an atom of sodium-23 have? Aha! What do? We take the mass minus the number of protons, and that gives us the number of neutrons. So what is the mass of sodium-23? 23. Okay, Moser, we get it. You don't have to make stupid faces at us. It's early. Okay, so we have 23 minus, how do we find how many protons sodium-23 has? Atomic number, which is? Sodium. Put your finger on sodium. It's Na. Sorry. 11. How many protons does this thing have? Or I'm sorry, how many neutrons? Good Lord. 12 neutrons. Okay. Easy peasy. You'll have some practice problems like that. Let's talk a little bit about how to write. Do you need me to go back for that? Let's talk about how we represent isotopes. So there are two ways to do it. There's hyphen notation and there's symbol notation. Hyphen notation just gives us the name of the element and its mass. So carbon-14 is carbon-14, carbon-14, hence why we call it hyphen notation. Sometimes we just use the atomic symbol, so we would say C14. And if I tell you that that's cobalt, go ahead and in your group, at your table, speak the name of this isotope. How would we say the name of that isotope? The slightly more complicated way to write isotopes, but definitely the way that gives a little bit more information about the atom in question, is what's called symbol notation. In symbol notation, you have the atomic symbol, you have the atomic mass up top, and you have the atomic number below. And those are given in front of the symbol. It gives you a reference on the number of protons immediately. So from symbol notation, you can pretty quickly get the number of neutrons by just subtracting the atomic number from the atomic mass. So let's practice one of those. If I have, so okay, everybody find potassium. Potassium, K? Can you find potassium? Okay, K, K. Haha, potassium is K. I have a whole bunch more, don't you worry. Do you want salt on your fries? You want any? Nah, my sodium's kind of high. Get it? Sodium? Nah. Sodium's Na. Okay, moving right along. So, you've got potassium, okay? If I have one atom of potassium, 40, how would you write that in symbol notation? Obviously, we're going to start with the K, finish it. So we have this loveliness for symbol notation. What I'm going to do right now is a practice sheet. The front of this practice sheet, the front of this practice sheet has got stuff that is all things we've just done. Now, you may say to yourself, Self, these are way too easy. This is ridiculous. I don't really need to practice these. 9 times through teaching chemistry now, and what I can tell you is Yes, they seem dead simple stupid, and what I can also tell you is that the little chart at the bottom throws the smartest kids. So really, you should practice it. Yes, writing nuclear symbol and hyphen notation is stupidly easy, but you're going to get points for it on the test. So hey, why don't you practice that skill? I will pass these out and then I will spy on you.